Okay, so let's go over our study guide here for our first 9 weeks assessment. I feel like you guys should be pretty good with this, but as always, feel free to send me any emails or questions, and I can send you some videos, maybe we can help you out with some things. Okay, but anyways, let's start talking about this. What trends are there to the periodic table? For example, from left to right, atomic number will do what? Well, from left to right, atomic number goes up. Give as many examples as you can see. Well, if we take a look here at the periodic table, if we look, so we have atomic number 1, atomic number 2, it definitely increases from left to right. But also, if you look here, we have 3, right? All the way down to 8, and then we get, I think, like maybe 3, I'm sorry, not 8, 3 all the way down to 10, this is 11. So we see the atomic number is also increasing, moving down. You gotta look for trends. So the size of the atoms is increasing from left to right, and the size of them is increasing, moving down. All right? Other trends we can talk about. We can talk about valence electrons. Valence electrons, as we know, start right here with our Roman numerals. We have 1, 2, we have 3, we have 4, we have 5, we have 6, we have 7, and we have 8. So valence electrons will increase as you move from left to right. Continuing here with other things, we know that the number of shells is determined by the periods here. 1, 2, 3, 4, 5, 6, and 7. So we know that the number of shells will increase moving down. Trends to the periodic table here. Let me see, we have those. Oh, we know that anything over here on this whole section, excuse me, I should say, this whole section, ignoring, of course, our hydrogen up here. I wish there was an easier way to do this. But ignoring that, this whole section over here and this whole section down here, they are all going to be metals. We know that anything over here on the right side is going to be a non-metal. And then down the stair-step ladder here, we're going to have our metalloids. All right? So, metals to the left, non-metals to the right, and we have the metalloids down there. Okay? But the main thing in terms of understanding our periodic table here is just knowing that from left to right, numbers of everything tend to go up. From top down, numbers of everything tend to go up. All right? And of course, vice versa for those. Valence electrons increase from left to right. Okay? All right, continuing here. Where am I? Right. Okay, so a column of elements share similar what? So a column are going to share similar properties or characteristics or chemistry. They are called families. All right. So using a periodic table, the element lithium will share its properties with what other elements? Well, if you look at lithium, lithium happens to be, and of course this is all messed up over here. Lithium is right here, so it's going to share all of its properties with everything else in its column, in its family. Do you remember the name of the family? These are the alkali metals. And if you can remember, we had a person on the screen throwing them into water and making them explode. And then we had somebody throw them into a toilet and make them explode. But they react very strongly with water. You'll notice, though, that this element here, hydrogen, is not included. We have lithium, sodium, potassium. I'm blanking on the other names right now as we go on down that list there. But regardless, these all of these right here are alkali metals, and they share common traits or characteristics. That's why they're a family. This guy right here belongs to not the same family, but the same group. Group number 1. There are a total of 18 groups all the way across here, vertical columns. But only some of them are families. All right, and not every family is an entire group. You can see that here. This one does not get included. Okay, because again, hydrogen is a non-metal. The only non-metal in that whole side of the periodic table. Keeping it rolling. Our metals, non-metals, or metalloids on the left side of the table. Metals are on the left. What are the elements on the right side called? Non-metals. What are the elements between these that are found in the stair-step ladder? Those are the metalloids. Which elements are more likely to be solids? Oh, metals are solids. I'm going to really encourage you to know that song. So we have our metals. Which ones are going to be gases? Most non-metals are gases. All right, so pretty much everything's going to be either a solid or a gas. If it's a gas, it's a non-metal. If it's a solid, it's a metal. Even some non-metals are solids, but don't forget your metalloids. All right, metalloids. They're going to be solids as well. Now, the following says, rank metals, non-metals, and metalloids from most conductive to least conductive. Well, the most conductive of these is going to be the metals. Metals are more conductive, and then non-metals are going to be the least conductive, which means metalloids, as always, are going to be somewhere in between. Okay? What are the Roman numerals used for? Roman numerals are used to show the number of Valence electrons. Those are the electrons on the outside. So valence electron is the electron on the outside. Remember setting up those Bohr models where we have circle of shell after shell after shell? Well, only the ones on the outside are used to be the valence electrons. Now, what's so special about noble gases? If you can remember, noble gases are all the way over here on our periodic table. And if you remember, everything over here is where everybody wants to be. And it's because of this rule. It's called the octet rule. All right, or the rule of 8. What it means is every element out there, all of these guys want to be like the noble gases because they have a full 8 electrons in their outermost shell. They have 8 valence electrons, and therefore that shell is full. And a full shell means a happy atom. So if you have a full outer shell, then that atom is going to be very, very happy. All right. Now here's the deal, though. Most of them are 8. That's 8. That's 8. That's 8. That's 8. That's 8. That's 8, and it's happy. But don't forget, this first shell, the first shell of an atom, only has 2 electrons. So helium, which is right here, is full when it receives 2. So the octet rule, as weird as it sounds, is when atoms are happy because they have either 8, 2, or in some cases 0. And that's kind of a weird distinction. But for right now, 8, 2, and 0 are our 3 reasons there. Excuse me. Label the valence numbers on this periodic table. Well, we have 1, 2, we have 3, we have 4, we have 5, we have 6, we have 7, and we have 8. We ignore these guys over here, these transition metals, because they are weird, and you will have to deal with them in chemistry, but you're not quite there yet. So you got a couple years before you have to worry about that stuff. Indicate the location of metals, nonmetals, and metalloids. We got our metals again over here, ignoring hydrogen. We have our nonmetals over here, all right, and including hydrogen, counts as one of those. And then you get your metalloids down the stair-step ladder right here, okay? Solids, gases, and then which ones are liquids? There's only 2 of them. Mercury and bromine. Mercury and bromine are our only 2 ones on there. Keeping it rolling. An atom's nucleus contains protons and neutrons. Protons and electrons in the atom are always equal. Everything must be balanced, right? So what makes something an ion? If protons and electrons are always equal, you have 2 protons and you got 2 electrons, then if you add those together, it always equals 0. Positive 2 and a negative 2 make 0. So what makes something an ion? An ion is something with either a positive or a negative charge. So if I have something with 1 proton and 2 electrons, it's going to have a charge of -1. Having an unequal number of protons and electrons makes it an ion. Typically, to make something into an ion, you take it when it has, let's say, 2 protons and 2 electrons, and you change the number of electrons in some way. You either add an extra one to make it negative, or you remove that extra one to make it positive. Okay, so it's adding and changing those electrons. Atoms gaining, losing those electrons, forming ions plus or minus. When you see those plus and minus. When the protons aren't equal, atoms turn into ions. When the protons aren't equal to the number of electrons, what we mean there. Draw a positive ion and a negative ion. Well, if I were you, I would do this with the simplest of all atoms, which is hydrogen. There's a positive ion. You have 1 proton and no electrons. Draw a negative ion. We're going to draw hydrogen, 1 proton, 1 electron. It's balanced. That's a normal atom. To make it an ion, add an extra one. This is my positive ion, and this is my negative ion, because I have more negatives than I have positives. Okay? Over here, more positives than I have negatives. What's the difference between an atomic number and a mass number, and why is it different? The atomic number is just the number of protons. The mass number is the protons plus the neutrons. Protons, neutrons find the sum that gives you the mass numero. The only thing about atomic number is, yes, it shows the protons, but it also shows the number of electrons, because those 2 things for an atom must always be equal. Okay? What particles are used to identify elements? Those are the protons. ID in atoms, protons, we count them. Carbon-14, for example, has how many protons? It has 6. It has how many electrons? 6. It has how many neutrons? 14, right? Because it says carbon-14? No, not at all. That's the trick. You just have to remember that carbon-14 is called carbon-14 because this is the mass number. Protons, neutrons, find the sum that gives you the mass numero. Protons, 6. Neutrons, unknown, gives me the number 14. 6 plus what is 14? 8. Protons, neutrons, find the sum it gives you the mass numero. That's where that carbon-14 comes from. That's the isotope name of carbon-14, including the mass number. So when an atom is called or named carbon-12, what's the 12? Well, we just said that's the mass number. Carbon-12 and carbon-14, why are they both carbon? Well, iodine atoms, protons, we count them. Because both carbon-12 and carbon-14 have 6 protons. So what's the difference then? If they both have 6 protons, what's the difference? Well, the difference is in the mass. This one has 2 more. But if it had 2 more protons, it wouldn't be carbon anymore. It would be fluorine, I think. Oxygen. But anyways, if it had 2 more protons, it would be oxygen. Again, iodine atoms, protons, we count. So if I want the same element, carbon, carbon both times, I can't change the protons. They both got to have 6. The only thing I can change is the number of neutrons. So you use 8 neutrons instead. And that's what an isotope is. Isotopes all have protons equal, neutrons are different. Just count them all. Okay? Please learn that song. I got people here in some of my classes who clearly don't know it, and you got to. Got to. Draw an atom. Where are the electrons? Well, electrons are around the outside in the electron shells. Where are the protons and neutrons? In the nucleus. In terms of this, don't forget, electrons are negative, protons are positive, and neutrons have no charge. What are isotopes? Atoms with the same number of protons, different numbers of neutrons. What makes uranium-235 different from uranium-238? 235 has a mass of 235. 238 has a mass of 238. They're the same elements, they're the same number of protons, so the only difference is their number of neutrons. Draw lithium-6, lithium-7, lithium-8. Which is the most common isotope, and how do you know? Well, if you look on your handy, trusty old periodic table, which everybody should, of course, have at their desk along with a calculator, and you look at lithium, you might notice that it says this. It says 3Li 6.94. And so in this case, the 3, the smaller number, that's how I know, that's always a smaller number, is the atomic number. That's the number of protons. Always smaller because it's just protons. This is the average atomic mass, which means we need to round it to 7. So it's no longer an average. Now it's just the mass number, the number of protons and neutrons. In this case, since I round to a mass of 7, that means lithium-7 is the most common isotope. That's why the average is more closely weighted towards the number 7. Remember, we talked about this with all those numbers and how you can change the average of something by how many of them you find. There are way more lithium-7s in the world than there are 6s or 8s. Therefore, the average lies close to 7. Okay? Keeping it rolling. Draw a solid, liquid, gas, and plasma particles. So, solid, nice, set, even, rows, all really close together. Liquid, still pretty close together, they're just jumbled up. For a gas, we got them all spread out, all kinds of different places, more room, go in different directions, more energy, etc. A plasma, however, I better see positive protons, negative electrons, or positive nuclei and negative electrons flying around everywhere. There's lots of positives, lots of negatives. That's a plasma. Okay? If you can remember my plasma ball, that was that little circly thingy that we had, that we could touch, and you saw all the little streaks coming off the middle part. It's a wonderful drawing there. But anyways, my plasma ball, inside there, you add enough electricity, and it turns the gas into positive protons and negative electrons that move everywhere. Okay? Which state of matter has a definite volume and definite shape? That's a solid. Because, again, they don't change. They keep that shape. Unless, of course, you break them. But on their own, they're not going to change. Which state of matter has an indefinite volume and indefinite shape? Well, since I can make a balloon get bigger or smaller by pushing on it, adding some pressure, right, and I can change its shape, balloons are filled with a gas. So that's going to be my gas. Which state of matter has a definite volume and a definite shape? I mean, I can try my best to squeeze water, but at the end of the day, it takes up a specific amount of volume. That water will always take up that much volume inside the container. So it's got a definite volume and an indefinite shape, because we know water can move around and take different shapes of its different containers. So that's going to be your liquid. Which one has the greatest density? Density is how closely packed the particles are. So that's going to be your solid, right? It's really closely packed. You have a lot of really strong bonds between the atoms there. Which one has the least density? That's going to be your gas. Particles are more spread out. How do you convert from one state of matter to the other? Pretty straightforward. Adding energy or taking energy away. Okay? Questions about pressure, temperature, and volume. If you have any questions about those, you should make/use the PTV strip. During your test, I would encourage all of you to get a sheet of paper, tear a strip off, put PTV on it, and you can have that on your desk. That will be okay. All right? Keeping it rolling. Let me see here. This is our pressure and temperature chart here. All right, so this above graph, you should be able to make predictions about solids, liquids, and gases using this. When I move left on the graph, so let's say I'm starting right here. As I move to the left, what is happening to the temperature or pressure? So as I move left, what's happening to the temperature? Temperature is on my x-axis, so moving left makes the temperature go down. What happens if I'm moving left to the pressure? Well, pressure is my y-axis. Am I moving up or down, moving left? No. Therefore, pressure stays the same. 0, no change. All right? What happens to the temperature and pressure when I move down? Well, let's find out. So right here, in fact, I can change it so we can actually do something here. We'll make our x right here. If I move down, what's happening to my temperature? Nothing. It's on the x. X's go left and right. So moving down doesn't affect my temperature. Well, if I do move down, though, it's going to make my pressure go down because my pressure is on my y. Down on the y is down for pressure. Keeping it going. What happens when I move to the right? Well, if I take my x and I move to the right, temperature is going to go up. If I move to the right, pressure will not be changed. Temperature goes up, pressure stays the same. What if I move up instead? So from my x here, and I move up. Temperature will not change because that's my x. Pressure will go up. How you move on this is very much dependent upon these x's and y's. You got to look at those first on any graph to know what's going on. Temperature is the measure of the kinetic energy of the molecules in a substance. So, rank solids, liquids, and gases and plasma from highest to lowest kinetic energy. Kinetic energy is the movement, the motion of the particles. Remember? So we have our solids, liquids, gases, and then plasmas, where these like actual gas particles come apart. Atoms shred into nuclei and electrons. They just go everywhere. But keeping this going, so I'm ranking solids. Solids have the least amount of energy, right? Liquids have a little bit more because you can finally break the bonds between the solids so they can move around a little bit. If you keep on adding more energy, it's going to break the bonds between the liquid particles, and then they can move freely. And if you keep on adding energy, they smash into each other and shatter, and the nuclei positive go one way and their negative electrons go another. A warm balloon is placed in a cold car. What will happen to the size of the balloon? If I place a warm balloon in a cold car, okay, I'm going to decrease the temperature. And if I decrease the temperature, that's going to affect the volume, right? And look at our PTV strip. If I use my PTV strip, let me make one for you here real quick. It's going to be hard to do here, I think, on my own, but we're going to make it work. I hope you can see this over here. Pressure, temperature, and volume. So in this case, pressure is going to stay the same. I'm going to decrease the temperature, and the volume of the balloon goes down. Okay, so putting a warm balloon in a cold car will make the balloon appear to shrink. A pressure in a 2-liter bottle is increased. What will happen to the temperature? So you'll notice volume is not mentioned, therefore it's kept constant. It's constant, you put your hand on it or your finger on it. The pressure is increased, temperature goes up. Keeping it rolling. With pressure, temperature, and volume, which two have an inverse relationship? That are the two on the ends. That's why they're on either end. Pressure and volume have an inverse relationship. That means if you hold temperature constant, when one goes up, the other goes down. And when one goes down, the other goes up. That's an inverse relationship. What is density? Draw an example of dense particles and less dense particles. Density is how closely packed the particles are together. Okay? And they can be very dense or again very spread out. Keeping this moving. How would this piston move to increase the volume? So if you look at this piston, we're talking about the volume of this area here. Okay? So if I want this piston to increase volume, I'm going to have to pull the piston out. That will open up more space. Does that make sense? If I want to decrease volume, I want this piston to go down. All right? If I want to increase pressure, our pressure and volume are inverses. So decreasing volume and increasing pressure are the same thing. Increase pressure, you push down on it. To decrease pressure, pull back. And decreasing the pressure increases the volume. It's the same thing. okay? If I want to increase temperature, well, if I'm dealing with pressure and temperature have a direct relationship. When one goes up, the other goes up. When one goes down, the other goes down. Direct relationships. So if I want to increase the temperature, push down on it. If I want to decrease temperature, pull up on it. And it's going to decrease the pressure. All right, let's take a look right here. And this is coming towards the end. Okay, good deal. Now, if we have the following, this is a heating and cooling chart. And the main idea is this. Anytime there's movement to the right, you are adding what? Heat. Okay? This over here on the y-axis, though, is temperature. And heat and temperature are not the same thing. Temperature is the average kinetic energy of the particles, how much they're moving. Heat is just how much energy you're adding. The more energy, the more they move, yes. But sometimes we use the heat for something else. So let's take a look. All right, right now, I'm in a solid form right here, okay? As I start moving up, I'm adding heat, temperature's going up. The solid starts out slow, adding heat, heats up, heats up, heats up, increasing the temperature. But then it gets to right here, and you get this zero slope. When you get to this zero slope right here, all of a sudden you see these words melting and freezing. Because when you get to this line here, even though the heat had been used to increase the temperature for a while, they move faster and faster and faster. When you reach that point, the bonds now start to break. And so the energy, instead of increasing the temperature, is now used to break the bonds. And so you slowly start to break the bonds. As you're adding heat, you're breaking the bonds between all the particles until all the particle bonds are broken, right, or at least mostly broken. And at this point, your solid has turned into a liquid. So once it's a liquid and they're moving around, then you need to increase the heat more. Increasing the heat more increases the temperature. They go faster. Temperature is the kinetic energy. They go faster. They go faster. They go faster. As it goes up, they're moving faster, moving faster, moving faster. Then you get here. They're moving so fast now the bonds completely break. And it starts going everywhere. And this is where we get boiling. So now the bonds are all starting to break, completely come apart from the entire amount of material until finally the liquid is turned into a gas. And so again, once it becomes a gas, then increasing the temperature is easily caused by the heat there. So the main idea is this. Anytime you have a zero slope, you are using the heat energy to change its state. Anytime you have a positive slope, here, here, and here, the heat energy is being used to increase the temperature. All right? That's how this works. So what happens at a zero slope? State change. What happens at a positive slope? Temperature's going up. Particles are moving faster. What happens as you move to the right? You're adding heat. What happens as you move up? You're increasing temperature. So you'll notice that sometimes there's no movement up. It's a flat line, meaning there's no temperature increase. Okay? Why is temperature not increasing even though heat is being added in places? Because temperature is not changing because they're changing state. So temperature's going to stay the same while the state changes. Once it's all changed, then the temperature will start going back up. But you can only use the heat for one thing. Okay, so it's either increasing the temperature or breaking the bonds. Now, the only thing on here, we need to talk about fusion and fission. I feel like we've gone over this a million times, but really quickly, fusion, all right, is when I bring together two particles. In this case, deuterium and tritium. And when they come together, what do they make? Helium. Where does this happen? In the sun. At all times. All the times. Therefore, this makes lots and lots of energy. Can we currently use fusion? No, we cannot. All right, and we can't use fusion because it's uncontrollable as far as we're concerned. It's too many millions of degrees. It happens in the stars, for goodness sake. So we can't use fusion yet, even though it would be great because it produces helium and lots of energy. In fact, fusion makes way more energy than fission. However, fission is the only one we can control. Fission takes something like uranium-235 and breaks it apart. So instead of taking two things to make one big one, fission is division. It's splitting into barium and krypton. When you split, you'll release lots of energy in the form of heat. And that heat is then used to create steam. Steam spins a turbine, which starts a generator, generates electricity, etc., etc. Okay, but the big problem is this. Fission is great because it makes lots of energy, all right, and it does not release any CO2. That's wonderful because currently fossil fuels are destroying our atmosphere. We don't want that. We would do fission if we could more often. However, the problem is that fission also makes these two things, barium and krypton, which are radioactive waste products. And we have to do what with those? Store them underground, deep underground somewhere where they will not bother life on the Earth. Because remember, radioactive particles can affect your DNA and kill you. So you have to be very, very careful with those. So we bury them underground in thick lead walls or put them in the hearts of mountains sometimes. Okay? So fission is used in our current power plants. Fusion is not. Fission is great, except it's expensive and makes a lot of nuclear waste, which is bad. But if we're careful, we take care of it, we can still use it and save our atmosphere the added CO2. However, if you want to do one thing to make billions and billions of dollars, this right here, fusion. Okay? That would be a big, huge saving grace for humanity in terms of energy. And I think that's pretty much it. Gamma rays are really powerful. They can get through lead, but only barely. You have beta particles, electrons, which can get through paper, but they can't get through plastic or aluminum. And then you have alpha particles, the bigger ones, the helium nucleus, the 2 protons, 2 neutrons, and they're really weak and really slow. They can't get through paper. That's it. That's all you got to know. I hope that helped. And if you have any questions, feel free to shoot me an email, and I'll see if I can send you some videos to help. Okay? All right. Appreciate you guys. I'll hopefully see you soon.